Good evening, guys. Let us start the session with next session with haloalkanes and haloarenes. Uh, this is the first chapter of the organic chemistry for your grade 12. Okay. Uh, okay. Before when we start this chapter, haloalkane and haloarene, you must understand that you should know the general organic chemistry, what we call as the GOC of grade 11. You must have a little bit of knowledge of your IUPAC names, general reactions of alkane, alkene, alkyne. Okay. Once you have done that chapter of grade 11, then you must understand, like, you can start this chapter. Okay. If you have a feeble memory of your previous grade knowledge, then you must go through the 11th grade syllabus first, and then you should come back to the haloarcane and haloarcane. Because the basics, the fundamentals, the key words which we are going to use in this chapter and onwards in this chapter, in this units of grade 12. Okay, we have studied in grade 11. So let's start with this haloalkane, and haloarene. Haloalkanes are obtained by replacing the hydrogen atom from alkane or benzene. That's supposed to be ethane, C2H6. So one hydrogen is replaced by any halogen. Okay, halogen may be fluorine, chlorine, bromine, or iodine. Okay, this is dihalide, dihaloalkane. This trihaloalkane. Similarly, you can have the haloarenes. Monosubstituted, disubstituted, trisubstituted. So alkanes here substitutes the hydrogen. You cannot consider a halogen as a functional. You can consider halogen or the halide group as a substituent rather than saying it a functional group. You have to call it as a substituent. Here we have a primary, secondary, tertiary. Look at this carbon, which is connected with the halogen. It's further connected with only one carbon. Say, for example, if I have a carbon, now this is a halogen X. Now X can be chlorine, bromine, or iodine. It can be also fluorine. But the reaction of fluorines are very, very reactive. Like fluorine is very reactive. So we get very few chemical reactions of the fluorine in the syllabus. Now, in grade 12, we have 1 to 2 reactions. 1 to 2 reactions of the fluorine. So if you see in grade 11th and 12th, there are hardly few reactions involving the fluorine. So they become very important for your board exams. Why? Because chlorine, bromine, and iodine. Usually you'll find this substituent groups very common. Oftenly they are used. But the fluorine is rarely you will find chemical reaction. So one or two reactions are there in the entire your syllabus, and they become very, very important. So anywhere if you find the reactions of fluorine, okay, automatically become very important. So if what I mean to say is if you find fluorine or fluorine related equations or fluorine related to give reason type of questions, you must have a pause. Okay, you have to stop and have to emphasize more on that particular topic. Why? Because they are very important. We will see in the coming topic. Now, here, halogen is connected with one carbon. The carbon is further connected with one carbon. This is primary halide. If halogen substitute carbon is further connected with two carbons, like here, this one, this is second carbon, then we call it secondary. Similarly, if you have halogen, which is the X, carbon, carbon, and carbon. This is a 3D halo. Okay, so this is how we call it primary, secondary, tertiary halides. allyl halides. What is the meaning of allyl? In allyl halides, if you see, the substituted carbon is connected with another carbon, which is sp2 hybridized. Remember, okay? If your substituted carbon is connected with sp2, that means a double bond carbon. Okay, we call it a allyl system. Similarly, here, if you see the halogen connected with the carbon, but further it is connected to another carbon, which is sp2 hybridized. This is allyl system. Okay? Benzylic halide, same in benzene. If you have CH, this is benzyl. Many students say get confused in phenyl group and benzyl. This is benzyl. Anything here is benzyl. This is benzyl. And what is phenyl group? Phenyl group is a benzene. That this is phenyl. This is your phenyl. This is your benzyl. Okay? Allyl nomenclature, guys. If you look into the syllabus, or if you see the pattern of the question paper of the board examination, you will find either one or two nomenclature in your 70 marks paper. Either the name will be given and they have asked that, okay, what will be the structure of that compound, or structure will be there and they will ask you what is the IUPAC name of that compound. Okay, so this type of question of nomenclature of organic compounds will never come more than, I guess, 2 marks. Maximum it is 1 mark, but you can extend it 1 mark to the 2 marks. Okay? So far, I have never seen any question paper where two IUPAC questions are asked. 1 mark is fine. So when you complete your entire syllabus, you can dedicatedly give a day practice for IUPAC naming of haloalkane. Now, what they usually ask in the IUPAC is they will give one halogen, say like bromine. Okay, along with bromine, there will be alkene. In. Okay? That means they usually ask two functional group or more than one substituent group. So here there is a one substituent group. They may ask you one more added functional group here. Say in this case, suppose if I have to ask, let me give the like OH. So the priority will go with alcohol group and then this. So you have to learn the priority of the functional groups as given in grade 11. According to that, you have to give the name to the compound. So not more than 1 mark usually they ask in the board. Usually the IUPAC's names are from the textbook only. So you must give attention to this all IUPAC names which are given in the see this type of structures will come usually. Draw the structure of the structural isomers of so compound like C5H11Br. What is the nature of carbon halogen bond? Carbon and halogen. This is carbon connected with the halogen. Let us say chlorine, Cl. Now, chlorine is electronegative. Electronegative. That means it tries to pull the electrons from the carbon. Carbon, in compared to chlorine, it is slightly electropositive. So what happens is it gives away its electron to the chlorine. So if you see this bond, between the carbon and fluorine, there is a partial negative charge, which we can say minus delta charge on fluorine, and there is a partial positive charge on carbon. So this bond is polar bond. So suppose if I have to attack this system with any nucleophile, nucleophile is either negative or have electron pair to Q. Nucleophile, the word has therefore nucleus loving. Nucleophile, phile means love. Okay, so nucleus loving, that is a nucleophile. Nucleus is positive in that. Hence, any species which attracts the positive particle is called the nucleophile. So, nucleophile has to attack, suppose, and it will not go on the halogen, it will go on the carbon. Why? Because nucleophile is negative and my carbon of haloalkane is slightly positive because of its polar. And in this, if electrophile has to attack, electrophile has to attack, and it will not select the carbon, but it will attack on the fluorine, that is halogen part, because electrophile is positive, electron loving, electrophile, electron loving. Okay. So this is a species here, carbon fluoride is negatively charged, so positive electrophile will attack on the fluorine. Now this is a simple mechanism which we have to remember while any organic chemical reaction. So here carbon and halogen bond is polar bond. Carbon has positive charge and halogen has a negative charge. You can see the bond between the carbon and fluorine. Okay. That is why we don't see many reactions of carbon and okay. Now this energy is quite comparable. Okay. In that fluorine is the next second electronegative element after the fluorine and bromine and then iodine. So you can see the bond enthalpy. Hence, bond enthalpy is less. The attraction between carbon and fluorine is less. You can see the gradual or fine increase in the bond because there is less attraction between the iodine and carbon. The bond length is highest and bond enthalpy is less. More the distance between the atoms, it is easy to break the bond. It is easy to break the bond. The energy required to break the bond is quite less. Now, let us see some methods of preparation of the haloalkane. Now, these are two very commonly used methods. Okay. Now, out of all this method, where you have to emphasize or which methods you must remember is the best method you can say you can remember this method. Okay, where X alcohol replaced by bromine and iodine. A hint I will give for this chapter is always remember the reaction of Br. There are many chemical reactions where you will find C and Cl does not work. Carbon and fluorine, we already studied that it has very few reactions where carbon and fluorine bonds can be broken and you can have some new reaction. There are Some reactions where carbon fluorine reaction also does not work. But if you take an example of carbon and bromine, anywhere you have to see the conversion, anywhere, even conversion or any explanation, any mechanism if you have to show, try to give with the bromine. Because in most of the haloalkanes, okay, the bromine actually works. Fine. So you can see here, see bromine and iodine. Okay. Now, this is the best example. This is arsenic board example, the last reaction. Okay. Why this is reaction important with thionyl chloride? SOCl2 is called the thionyl chloride. Why this reaction is very important? Preparation of alkyl halide. If you see the product so formed here are gas. SO2 and HCl are the gaseous state. Okay, so what happens is they move out of the system very easily, and hence your alkyl halide is left behind. Okay, so they move easily out of the system, and what is left behind is RCl. Whereas in all these reactions, you have to purify your alkyl halide by removing this component, extra component by byproduct. Okay? See here, free radical mechanism, how you can prepare the haloalkanes. Now,
You're not audible still.
That one. Hello. Hello. Am I audible now?
Yes, yes, sir, now audible.
Oh, fine. So we were just discussing about how this method of free radical mechanism is not a preferred choice for making the haloalkane because it gives a multiple products. Multiple products. What is the problem with the multiple products that we cannot separate it easily. That means there is an additional cost. Okay. So in a real world, when we go outside, uh, additional cost creates a problem. Okay. So main product is less with so many substituent or the byproducts. Okay. So it is not a good choice. Now let us see some other methods of preparing alcohol. This is an electrophile substitution method on benzene. Now, why many times the students simply confuse that why only electrophilic reaction on the benzene? Benzene is having three triple bonds. Now, electron on the benzene, because there is a three double bonds, you can call it the electron deficient. Deficient means it requires negative electrons. It is in need of negative electrons. So you will say, sir, okay, there will be a good reaction between nucleophile and the benzene. Because benzene does not have good enough electron, that is why it has made three double bonds. So when there is a chemical bond and carbon is not getting electron from outside, what the carbon does actually is they make the double bond within. That is why double bonds has formed because there was no other element coming and helping the benzene to give the electron. So what the carbonate decided, okay, if nobody else is giving the electron, let us share our own electron and make a bond. That is why there is a double bond you can see. That means it's an electron deficient compound. But electron deficient, being in an electron deficient compound, it does not welcome the nucleophile. Why? Because if you look at the structure of this benzene, on the benzene, if you see now how the double bonds are formed. This is a pi orbitals of the carbon, which is forming the double bond. So this is one. This is total three double bonds are formed. If I see the structure as hexagon, okay, or let me again like this. First, this is the six carbons, and their pi electrons are making double bonds. So if you see the upper lobes, all these lobes upper, they make a cloud, negative orbital cloud, one above and one below the benzene. So you can see there is a one hexagonal, there is a hexagonal plane, there is a benzene, and there is one donut. You can see as a donut. Okay, this donut shape electron cloud, one above the benzene, one below the benzene. So what will now nucleophile face? If the nucleophile has to come, this negative cloud will repel the nucleophile. The nucleophile cannot come on the benzene from either side. So nucleophilic reactions are prohibited on benzene. So what is now left? This clouds will actually attract the electrophile. So on the benzene, electrophilic substitution. Substitution means we have a hydrogen. There are six hydrogens on the benzene. I'm trying only one hydrogen. So electrophile substitute this hydrogen. Okay, and gives me a electrophilic substitution reaction. Once the electrophile comes to the benzene, there is no positive charge. Okay? Fine. This is electrophilic substitution. This is what now we have to see by electrophilic substitution. Now, what we have to understand, what we have to learn is how to prepare few electrophiles. Suppose I have toluene. This is CH3 benzene. Okay, methyl benzene, or you can call it toluene. Now, toluene is a common name, but this common name is accepted by the IUPAC. So it is also an IUPAC. It is also a IUPAC name as well as a common. Okay. Now, suppose you have to put chlorine. I have to put chlorine on the benzene. So these are few possibilities: ortho substitute or para substitution. So simply I cannot react it with the chlorine. Because the chlorine is not going to give me Cl plus. We just have understood that electrophile will go on the benzene or substituent benzene. So toluene is a substituent benzene. Methyl group is substituted, okay, the hydrogen. The substituted benzene, I have to prepare first electrophile. Now, you may surprise that we have never seen Cl plus. Usually we see Cl minus. So how to prepare Cl plus? Okay, so Cl plus has to be prepared. Say for example, Cl2, Cl2, let me write it like Cl2 reacted with AlCl, aluminium chloride. Now, aluminium chloride is a highly electron deficient compound. It does not have the electron. So what happens is it attracts Cl minus, Cl minus on Alc. So what happens is it forms AlCl4 with the minus charge. So once the Cl minus goes on the aluminum, okay, and what is left behind is Cl plus. And what is left behind is Cl plus. This is left behind. Similarly, suppose if I have CH3Cl and if I react with AlCl, what will happen? It will attract Cl minus, will form CH3 plus and AlCl4 minus. Or else if I react CH3C double bond OCl and react with AlCl3, what I will get? I will get it will absorb Cl minus AlCl4 minus and I will get C double bond OCH3 plus. Okay. Now, all these are the electrophiles. Here Cl plus is electrophile, here CH3 plus is electrophile, here carbonyl, alkyl carbonyl is electrophile. Now, this all electrophile goes and attacks on the benzene. See, for example, benzene, we can call the substituent benzene toluene, okay, reacted with Cl plus, will get chlorobenzene, will get either ortho or para. Now here you will get more of para because this is more symmetrical. This compound is major because of its symmetrical structure. If you react with CH3 plus, you will get CH3, CH3 again. Here you can see para dichlorobenzene, the dimethylbenzene is more symmetrical, or you can have acyl group CH3CO plus that CH3. Okay, so this is how we get the reaction with benzene. This is another reaction like Sandmeyer reaction. This is a Sandmeyer reaction. The Sandmeyer reaction we have to prepare first benzene disonium salt. Benzene disonium salt. How it is formed? Aniline reacting with NaNO2 plus HX. Actually, we need a HNO2, nitrous acid. Aniline plus nitrous acid. Aniline plus nitrous acid. But nitrous acid is not a stable acid. It converts into nitric acid. So what we have to do is during the reaction, C2, we call it C2, SiC, C2. During the reaction, we have to prepare the HNO2. How we prepare it? Sodium nitrite plus HX, that is a hydrogen halide, 0 to 5 degree. It is very, very important temperature condition. 0 to 5 degree centigrade, or you can convert it to Kelvin like 278 Kelvin. If this temperature is not maintained, you will not get a good yield of disonium salt, benzene disonium salt. Diazo. Diazo means this is a diazo group. This is diazo group. This is by connecting here with the benzene. Diazonium chloride. This is chloride. This is diazo group. And this is benzene. So benzene diazonium chloride. If Cl is not there, we just simply call it benzene diazonium salt because it will be having a positive charge. So Cu2Cx, when benzene disonium salt is reacted with Cu2X2, this is the classical reaction, we call it Sandmeyer reaction. It's a name reaction which is in syllabus. Very important reaction. Cu2X. Now X can be here Cl or Br. Okay, you can surprisingly F and iodine does not participate in the reaction. Okay, so X is Cl and Br. That is why initially in the starting of the class I said any reaction which you have to learn, always remember in case of Br, because there are many reactions where chlorine, iodine, or in some case of fluorine also does not participate. But bromine is the halogen which is found in almost all alkyl halides mechanisms. Okay, so prefer bromine as a halide group while mentioning or by remembering any example during your preparation. With Ki, you just have to simply add Ki and shake the solution with disonium salt, and you will get the benzene iodide from alkene. Now, this reaction occurs with the HX. Okay. The halogen goes into the carbon, which is having less number of hydrogen. Markovnikov rule. Remember this as a Markovnikov rule. Okay. HX again HBr. Markovnikov rule is shown by bromine only. Remember this. Many students make a mistake. They write HCl and get confused that Cl will go to that carbon atom which has a less number of hydrogen. No, HCl is not a participant here. Okay, always remember for Markovnikov rule, it is always and only Br, even not iodine. Okay, so remember that. If you an alkene, suppose Br2 with Cl4, which is a non-polar solvent, okay, you will get the dibromo derivative. Few in-text examples are there, so go through it. Again, a very important name reaction here. Alkyl head is a displacement reaction. This is halogen. Now, this is iodine. Now, if you see the reactivity, fluorine is more reactive than fluorine, than bromine and iodine. Why this reaction is important and why this reaction are usually asked? Remember this reaction. Okay. Now, we have learned that a more reactive element displaces the less reactive element. But in this reaction, if you see, iodine is less reactive. See the reactivity of iodine. From all halides, it is the least reactive. But what it is doing, it is displacing the more reactive element. And that makes the beauty in this reaction, that why this reaction is very important. Why? Because here the less reactive element is displacing the more reactive element. So we do not have to focus much on the mechanism, but yes, here we have to use a triacetone. Okay, triacetone as a solvent. It is there in the book. Okay. So NX, say for example, NaL. Why dry condition? Because if there is a water, the water will break down NaCl or NaBr or NF, and this Cl minus or halide will behave as a nucleophile. It will displace the iodine because these are more reactive. So chlorine can easily displace iodine here, and there is a very much chances that you will find the backward reaction. Okay, in that case, what will happen? The backward reaction will proceed backward. So triacetone actually it is used as a solvent and also prevents the backward reaction. Okay, again see here, you can see Cl and Br. Okay, chlorine is not there. Now look at here. Next is the Schwarz reaction. The above reaction is called as the Finkelstein reaction. The second reaction is Schwarz reaction. The Schwarz reaction, what is the see, chlorine? I just said in the class, starting the class, that there are one or two reactions in the entire syllabus where the fluorine is there. Okay, so this reaction becomes an important reaction in itself. Why? Because in your entire syllabus, there are one or two or maximum three reactions. Okay, as far as I know, there are only two reactions to the fluorine. Remember that, and this is one of that. And because it's one of the rare type of reaction, this reaction becomes an important reaction to be asked in the board exam. Okay, so do not forget this is Schwarz reaction. You must remember. Okay, the bromine or Cl or your iodine get replaced by the more reactive F, and you will get the fluoride, alkyl fluoride. There are some again index questions we must go through it. Physical properties of the haloalkanes, because melting and boiling point are literally comparatively higher. Why? Because this is negatively charged, this is a positive charge. Okay, so there is a polar bond is there. What happens to two halide molecules? This is positive, so there is a dipole-dipole interaction between two alkyl halides. So there is an attraction. Okay, so compared to their parent hydrocarbon, the melting boiling points of haloalkanes are comparatively higher than their parent alkane. Okay. If you have to compare the boiling melting points internally among the iodides, then iodide has the highest melting boiling point because of its size. Iodine is bigger, fluorine is small, and chlorine, then bromide, and then iodide. Because of the higher size, it is difficult to displace. You can easily assume that if you're moving an elephant, elephant is sitting, and if you are pushing it, it is very difficult. The pushing a small goat is easy. So that fluorine is a goat. You can easily displace it. You can move it from its position. The iodide is a bulky element. So hence its melting boiling points becomes little higher in its halide groups. This is a comparative graph. You don't have to remember this graph and the data which are given in the book. As till today, the data are not asked. Now, this is a primary bromide. Okay, how the primary bromide, this is a secondary bromide, and this is tertiary bromide. Okay, because primary halides are having a more surface area, so the more van der Waals force is there, so boiling melting points are comparatively higher. The secondary 2-degree halides are having less surface area, and tertiary halides are having further less surface area. So this is the example where you can explain how the surface area of the alkyl group actually play an important role in determining the melting boiling point of any alkyl halide. So more the surface area, higher the melting and boiling point. Now here This is again asked in the board exam. Look at this. This is dihalide derivative of 15. Dichlorobenzene. 1,2-dichlorobenzene. 1,3-dichlorobenzene. 1,4-dichlorobenzene. Now, if you look at the boiling point, look at this one. 453, 446, 443. Highest in why? Because why 1,2-dichloro? Why 1,2-dichloro benzene is having higher boiling point? So if this is a plane of symmetry, look at this. I have drawn one line which you can see as a symmetry. So one part of this molecule, this part of the molecule, because of the presence of the halogen, is quite negative, and this part of the again this dotted part, you can say, is quite positive. So there is a this molecule is a polar molecule. Now the polar molecules are having higher melt boiling point. Okay, so if you compare the boiling points, highest amount. Now melting point. If you look at the melting point, look at this para. Okay, these are para derivative. Why this para derivative? Because in the solid state, if you see, this is more symmetrical structure. Look at this symmetry. The more symmetrical structures easily forms a good symmetry or good lattice. Okay, a good solid structure. So the symmetrical structure like this also, sorry, para dichlorobenzene fits good in the lattice structure, and hence a good crystal is formed, and hence you will find the melting point is higher for para dichlorobenzene, but in the boiling point you will find the ortho is having higher. So this is again a very nice give reason type of question. Okay, and not asked in recently board exams, but yes, if you see the 6 to 7 years back, some question papers will find this give reason type of question. Solubility, halides are insoluble, usually slightly soluble in the water because of its polarity. But as the carbon chain increases, the non-polar part increases, the solubility decreases. Okay, but as of now, on simple note, you can say the alkyl halides are not good soluble in water. Okay, they are quite soluble in the non-polar solvent like CCl4 or carbon disulfide, nucleophilic substitution reactions, SN1 and SN2. Now, SN1, SN2 mechanism, guys, you have to really understand, okay? Because almost all the chemical reactions in organic chemistry are dependent on these two mechanisms, SN1, SN2, okay? And because this is one of the basic fundamentals of any mechanism, SN1 or SN2 type mechanism. Okay, in board exams, SN1-2 mechanism and SN1 mechanism, they are asked. A difference between SN1 and SN2 as asked. Okay, you must do. This is a must-done topic for your board exams. So it's a simple mechanism. Okay, go through it. You have to understand it. Okay, in SN1 mechanism, one hint is there, like SN1 mechanism, what happens is a carbocation is formed. Carbocation is formed. Now, this is carbocation. Now, whenever we make a carbocation, you must take a pause. Do not complete the reaction. Don't get hurry in completing the reaction. Okay, even if you know the answer, take a break there, take a pause. Look at the carbocation and think, okay, can you make the further stable carbocation by hydrogen shift or alkyl shift? Okay, suppose if you are having, say for example, this is a carbocation. Okay, suppose this is a carbocation form. This is a primary carbocation, and suppose there's a nucleophile. Let's say bromide. Don't be in hurry that okay, this bromide will go on this carbon. No. Okay, what happens before this nucleophile or bromide attacks on this carbon? there is a methyl shift. This carbon will go on this carbon and it forms a stable secondary carbocation. If there is a chance of making a tertiary carbocation, then make it first. So if there is a primary carbocation, think, stop, and try to make the secondary carbocation first, and then show the nucleophilic addition. If there is a secondary carbocation, take a pause and try to make the tertiary carbocation by hydrogen or any alkyl shift. If there is no such possibility, then it is fine. You can continue the nucleophilic reaction. But if there is no possibilities of shifting hydrogen or any alkyl group and making the further stable carbocation, then you must do it that first and then show the nucleophilic reaction. Because in carbocation, third degree, 3 degree is more stable than second and then primary. Okay, so this is a hint which you have to remember. Usually in the board exams, uh, alkyl shift and hydrogen shifts are not frequently asked, but in your entrance exams, like NEET and JEE, this type of questions are asked. Okay, this examples in text questions are very important, very important. In fact, the board does not even take enough pain to change the structure of this molecule. They simply copy from this in-text question and paste into the board exam. You'll find this examples 10.6, 10.7. In newer publication, this example might be different. Okay, the number may change, but the question does not change. Okay, question does not change. Copy paste questions have been asked in several past year board examinations. So you must go with these examples. Okay, remember these questions. They are simple examples based on SN1 and SN2. No need to explain, but yes, they will ask you, okay, arrange the following alkylides in decreasing order of their reactivity. So you have to. Chiral carbon and optical activity. The definition you have to remember what is a chiral or chiral carbon atom. You have to remember these are asked in the board exams. What is racemization? Okay, again, it is a very commonly asked question. Racemic mixture. So in this all pages, we'll find what is a 50-50%. Okay, dextro and levoretoric compound. See here are called the racemic mixture. So these are some common definitions which are actually asked in the board exams previously. Retention, inversion. Okay, these are common terms. In 3 markers, these few terms are asked from this chapter. These questions are, as far as I believe, these are the questions which are student-friendly questions, which the board wants that, okay, that every children should appear. Because these are the common questions, very easy questions. Okay, retention and inversion. If you know the SN1, SN2, you can easily answer what is retention is, what is inversion is. Okay, if you know the optical activity, you can easily explain what is dextro levorotatory compounds and the racemization. Okay, so these few terms are frequently asked questions in the board exam. So with this is elimination reaction. Mechanism is very important. Okay, so chemical properties, guys. So far, it's already 5, 6, now 45 sessions over almost. Okay, so in the next session we can continue with the chemical property of the alkyl halides. So far, what we have done is the basics of alkyl halides, and what we have done in this class, you can expect around 3 to 5 marks questions. Okay, what we have done in this chapter is around 3 to 5 marks weightage can easily come from this portion what we have done. Though we have not done the SN1 and SN2 mechanism in detail because it will take again in one entire class. to understand. Okay, so from the textbook, okay, I will suggest that go through it and understand, explain it, write it, and try to understand it. So because all your chemical reactions now onwards from this topic, okay, are based on your SN1 and SN2 mechanism. SN1, SN2. Okay. So, shall this for the next class, we'll start from here, the reactivities of the alkyl halides. Okay. There is a doubt.